Exercise 22. Consider the following problem. Determine the minimum value of z, where z equals 0.6x minus 0.3y, subject to 44x plus 60y greater than or equal to 165, 1.1x minus 1.9y less than or equal to negative 2, 4.8x minus 3.8y greater than or equal to negative 20, and 2x plus 3y less than or equal to 24. Part A. Is this a linear programming problem? Explain the basis of your conclusion. Well, determine the minimum value of z. Okay, it's an optimization question. Here's the formulation of z equaling 0.6x minus 0.3y. Well, z is a linear function of x and y. Okay, another requirement satisfied for a linear programming problem. Let's take a look at the domain, the allowable xy's. What have we got here? Inequalities are restricting it, and each inequality here is linear. And each inequality is of the one of the three permissible types. In linear programming, you need to have either greater than or equal to, or less than or equal to, and we've got that going on here. Okay, let's write our statement for part A. Okay, so there we go. Yes, this is a linear programming problem. It concerns the optimization of a linear function, and the domain is defined by a system of linear constraints, each of which is one of the three permissible types: less than or equal to, or greater than or equal to. Alright, going to part B. If this is a linear programming problem, yes, then solve it with assistance from the TI Nspire CX. Round all final numbers to 3 significant digits. Well, let's see. For solving this kind of linear programming problem, it's a real valued function of two variables. The domain here is going to be some region in 2-space in the xy plane. That's something we can get going on the calculator here to get started. Before we do that, though, we need to have the inequality in the form y isolated. In other words, y less than or equal to, or y greater than or equal to some expression in x. So let's get started here doing that. I suppose we could kind of organize matters a little bit. Let's label this. Here's inequality 1. Here, inequality 2. We can refer to this inequality 3, and this inequality 4. Okay, so here we are going to rewrite inequalities, and let's take 1. Now we need to solve for y. In this case, we see we could subtract 44x and divide both sides by positive 60. Alright, and in those algebraic operations, we leave the greater than or equal to sign alone. We would have y greater than or equal to 165 minus 44x divided by 60. Okay, let's go on to inequality 2 and get this prepared for calculator usage. Okay, alright, let's first, a little complicated, so let's first subtract 1.1x from both sides. So that would leave us with negative 1.9y less than or equal to negative 2 minus 1.1x. Alright, our next step. We could divide both sides by negative 1.9. Now, with an inequality, if you divide both sides by a negative, you must reverse the inequality. So we'll do that as well. And I'm going to distribute the negative sign through this numerator as well, leaving us with y greater than or equal to, right? There's the reverse of the inequality sign. And here I will call this 2 plus 1.1x divided by 1.9. Okay, let's go to inequality 3. Here, looks like we could subtract 4.8x from both sides as a first step. Okay, so that would start off with having negative 3.8y greater than or equal to negative 20 minus 4.8x. Now, let's divide both sides by negative 3.8. It's an inequality, so we got to remember to reverse the inequality sign again. Y less than or equal to, there's the reversal. And I'll take the negative sign and distribute it through this at the same time. That will give us 20 plus 4.8x divided by 3.8. Okay. Let's move on to number 4. Inequality number 4. Okay, pretty easy here. Subtract 2x from both sides and then divide both sides by positive 3. No need to be worrying about reversal of inequality signs there. We have y less than or equal to 24 minus 2x divided by 3. Okay, we're ready to go to the TI Nspire. Okay, got the TI Nspire opened up here. Let's open up a new document and we will add a graph. Something to do first. This question, remember, asks us to round final numbers to 3 significant digits. Okay, now this graph of the domain or feasible region is going to be part of the numbers we use towards the calculations, and since we want the final calculations to all be accurate to 3 significant digits, the inputs should be at least 5 significant digits to avoid intermediate rounding. So a little preparation first. In fact, let's go back to the home screen. Let's get the go to the settings here and graphs and geometry. We want to have a floating 5, giving us 2 extra digits there. I'll mark that OK. And now we could proceed to our document here. Alright, now we have got these inequalities written. Getting ready to graph an inequality, first thing we have to do is actually backspace there and change that equal sign to, let's see, inequality 1 has a greater than or equals to sign, 5, and notice it changes from an f of x notation to a y, because we're actually graphing a relation now, not a function. Anyway, to record what we've written here for our number 1 inequality, that's going to be the parenthesis and the 165 minus 44x, then our parenthesis, and divide by 60. Okay, enter that. Alright, there we are. Hang on. Let me click label so it for sure stays around. Alright, now I'll move it to maybe a more convenient location up here. Okay, great. That's one inequality. I'll push a tab, bring up the formula bar here, and now we go to the second inequality. Need to delete that equal sign again, and our second one we rewritten as a y greater than or equal to, alright, number 5, y greater than or equal to, and we have here a parenthesis 2 plus 1.1x, and let's see, all of that is then divided by 1.9. Okay, enter. Alright, we have this now. Now, so far, the domain is right in this angular region here. Okay, I would like to see the label on this, so maybe I will right click and choose 2 to assure the label stays around, and I'll put this over here, I suppose, for now. Okay, well, we kind of keep track of things as we go here, so that we will know what the overall intersection is. Again, right now we've already been reduced to right in here, this angular region here. Let's go ahead and bring up the formula bar again, tab, and once again it's an inequality, so delete that equals sign with a backspace or a delete key. And number 3 is a less than or equal to, okay, number 1, and it is a y less than or equal to, we got the parenthesis, 20 plus 4.8x parenthesis, and divide by 3.8. And enter. Okay, so we know that we were reduced to this angular region. Now with this other inequality, it's in this region that it is here, this shade of blue here. Kind of keep track of this, and let's get the label to be available. Let's see, maybe putting it down here is kind of next to the blue line, yet still out of the way. Okay, so far we're trimmed down to this much here. Okay, we have one more inequality to enter. Let's hit that tab key, bring up that formula bar again, and as before we need to exchange this for an inequality sign. Number 4, we rewrote it as a y less than or equal to, okay, number 1, and parenthesis, we need 24 minus 2x. Parenthesis, divide by 3. Enter. Okay, now instead of this overall region, it's been cut back to just this quadrilateral here. Now let's see what we can do is we will kind of select and pull down the graph a little bit to get our domain or feasible region in plain sight. Let's see, maybe about there will be pretty good. Now that we've done that, we could make sure that these labels are maybe a little better positioned. This green one near to the green line. This blue one I think would look maybe better over, oops, over here, if it'll stay. Okay, and how about this new red line? Let's get its label on here. Hold on. Label. Oh, okay, here we are. This could be moved to, maybe up here. Okay, and I think this green would look maybe better down here. Okay, now that we have this, we've sort of mentally kept track of this region here. We're going to make this look nicer when we finish, so we have some more work to do. One thing really important about these regions are the vertices, of course. That's very important to linear programming because we know that's where the maximum and minimum will occur in this case, bounded, non-empty domain here. So we know that our linear programming problem has both a maximum and a minimum, and each occurs at a vertex. So time to get vertices. For that, we could go to the menu here and choose points and lines, intersection points. Okay, now here you're supposed to pick 2 lines. Okay, right now that graph looks good, and this graph looks good, and I could push enter to have that point of intersection labeled right there. Nice. Let's go over here, select this graph and this graph, wait, and that graph. Oops. How about selecting here and there? Okay, there. Now we get those 2 graphs selected, and push enter to lock in the labeling of that coordinate there. And this graph. Okay, there's the point of intersection, and enter. Okay. One more to do here. Okay, this graph and that one already apparently selected. Push enter to ensure it gets put on the graph here. Okay, now we have these 4 vertices here. Let's see, to make this look clarified, a few more things. I suppose we could move the okay, I want to exit this tool, I should say, before we go further. So let's go here and escape. And escape. Now we're no longer using that intersection tool, and we can focus on just making these point labels be put in better locations. Let's see, maybe first move this blue label down here a bit. This intersection point might be best labeled over here. That would be probably a good place up there. This label maybe further off to the side. Those 2 labels look good. This green label, there, grab it, and up here. Okay, so the vertices are in pretty good locations for their labels. A little fine tuning here. I want to get this right there, and let me actually move this up into the corner and bring this label up here so it's not in the feasible region with its text. Okay, I think that looks pretty nice. Now I want to very clearly show this domain or feasible region. So here would be a good chance to sketch a quadrilateral. So here in the menu, let's go with shapes, and okay, polygon. We're in that category. Okay, it started drawing a little too quickly here. Let me escape the tool for a minute and go back. Oh, the tool's still active. Okay, let's get it started then when we have a point that we like. Okay, there, it's pointing to one of our vertices. I click there, make that one of our points of this polygon. It's pointing to that point of intersection. Good. Click again. There. And there. Okay. Good. There. Get that like so. And now it's time to escape the tool there. Now, let's go to this polygon and make it look nicer. Right-clicking. For colors, let's have both its boundary line and the interior itself be bright red. So I've chosen that. Now that takes care of the boundary of it. Right-clicking, going to color, fill color, also red. Okay, now another thing. It's a little bit too color rich here. The feasible region's not quite standing out prominently on the graph like we want it to. Now what I really need are the boundary lines here, not these inequalities. So what I'll do to clean this up is I'll actually go back to the formula line. So hit tab and let me expand this entry line. Alright, starting here for instance, clicking on that, and let's go back a space and then delete, turn that into just an equal sign. Now there's that little extra dot there which has to be removed. I don't know why it does this, but I always have to remove this as a separate step. There, now it's y equals to that quotient there, and hitting enter, that will fix up one of those, and we will continue to do this with all 4 of them. So this one here, back up, delete the inequality, make it an equal to just have the boundary line, and take care of that little extra multiply by sign there that's not necessary. So backspace and enter. Okay, now to another one right here. Let's go back there, delete that, make it equality, delete that extra multiplication sign, and now we have that. Okay, we have one more inequality to turn into an equality, so then just boundary lines appear, and tab, expanding the entry line, and let's see here, it looks like we should, there, click an arrow up to expose it, and starting here, backspace, equality, delete that little equal sign, enter, okay, there. Now our graph is looking pretty sharp. The feasible region now very clear and prominent. Nothing else is shaded elsewhere. And the other remaining detail might be to give this some labeling. So let me pull up the text tool here, and this is domain, or it's a domain. Generally speaking, since we're in the realm of linear programming problems, these tend to be called feasible regions, so we'll label it that way here, feasible region. Okay, and let's see, how about moving this maybe right there. Let's see if that looks okay. Okay, looks pretty good. Got our feasible region, all the vertices are quite clear. Looks like we're ready to proceed from here. Something else we should do. We did quite a bit of algebra at this point, and maybe there's a mistake here. We have to have the feasible region right. Okay, let's do some sort of check here, something simple. Okay, since we have a graph of it here, maybe we grab a point that's clearly in the feasible region and substitute into the original inequalities and make sure that it yields true statements throughout each case. Alright, now we want to pick an easy point. And here's something you might want to do in case you get a region where, is this easy point in it, or is this not? Just to show you this, you can go to the menu, and on the view, we can show the grid. The grid is nice because it shows you exactly where points with integer coordinates are appearing. For instance, right now, this point that the little index finger is pointing to, that's of course now in our region, and we can notice that those coordinates are, let's see, 1 and 3. Okay, so no doubt about it, 1, 3 is in our feasible region. Let's take that idea and go back to the original inequalities and start checking things over. Okay, so here we have a check of feasible region. Alright, so we have here that 1, 3 is an element of the feasible region. And so we will substitute it into each original inequality. Remember, mistakes could have been made in any of our rewrites here. All it takes is one little negative sign and the whole problem can go out of control. Okay, so we want to make sure we do something like this. Alright, let's go to 1. In the case of 1, looking at the original now, we have 1 for x, 3 for y. We can do it mentally in a lot of cases here. So that would be 44 by 1, 44, plus 60 by 3, 180. See, that's why you pick a point with easy coordinates, so then you can just do easy mental arithmetic here. How about that being greater than or equal to 165, 180, add 44, big number, clearly bigger than 165. This is true. Okay, let's go to original inequality 2. It's right here. 1 for x, 1.1 then, minus 1.9 times 3. Let's see, 5.7. Is that less than or equal to negative 2? Well, this is going to be like a negative 4.6 or so. That's less than negative 2. True. Okay, let's go to the third original inequality. X is 1, so that means 4.8 minus 3.8 times 3. Let's see, 4 times 3 would be 12 minus 0.6, 11.4. Is that greater than or equal to negative 20? Okay, this will be about like negative 7-ish or so right here. You don't even have to do the entire arithmetic to evaluate just an inequality, and negative 7-ish or so compared to negative 20. Okay, it says greater than negative 20 for sure. Okay, that's true. Number 4. So far it's looking good. Okay, easy inequality here. 2x, that'd be 2, plus 3 by 3, that's 9. How about that? Less than or equal to 24. True. Okay, we get a check on our feasible region, at least with this. It's not a bulletproof check, but it uncovers most of our errors, we would like to think. Alright, let's go back and return to the calculator portion of this question. Okay, so we're sitting with this nice, very complete feasible region graph. It's time to do what? Time to evaluate the objective function at each vertex here. We're going to do this really accurately. So an idea here would be to, let's see, let's start with this vertex here. Now what I'll do is I'll click once, click twice, and this allows me to copy this number. So copy is Control C. I've got that first x coordinate. Now what I want to do is I want to add a spreadsheet. So let's go with Control Add Page, Spreadsheet. Alright, right here. And then we can go Control Paste. Alright, we got that. That'll be our x coordinate, and we'll keep that in this first column. We could start here and actually label these columns another way. It's labeled column A, but it helps whoever's reading our solution might appreciate something like x coordinate of the vertex. So x, and to get it underscore here, let's go there, underscore vertex. You can't use blanks in the naming of a variable, so that's why I need an underscore there, and we'll say VERT there. X coordinate of the vertex will be the label of this column. And while we're on this kind of idea, we can similarly, analogously label this as a y coordinate of the vertex. So it has a choice of names, either A or B. And now we're prepared to capture this y coordinate here. Let's go back to the screen here. Here we are. 2 clicks, it's ready to be copied. Control C, and let's go back to the spreadsheet page, and now Control V puts it in there. Okay. Next vertex. Go back to the graph here. All right, let's go kind of counterclockwise, the positive direction in circles in math. Okay. Click once, click twice. It's ready to be copied. Control C. And now let's go back to that page and Control V. Pastes it. Okay. If you tab, it will... Oh, no. Never mind. Let's just go like that. Prepare for the y coordinate. Back to this first page. And let's take the y coordinate here. 1 click, 2 clicks, ready to be copied. Control C. Back to this page. And Control V. Okay. Back to this graph. Okay, ready for copying. Control C. And here to the x coordinate of the vertex. Paste. Control V. Okay. Back to the graph. Click once, click twice. Oops. Hold on. Let me do once, twice, there. When it's highlighted in blue, it's ready for copying. And then back to here. Control paste. Alright, one more vertex to go. It says to here. 1 click, 2 clicks. Ready for copying. Paste. Y coordinate. Ready for copying. And paste. Alright, there's all the vertices. Now, it's time to compute the z value, each vertex here. So we could come to C if we wanted to, first of all, maybe we want to label it with something more descriptive than, in addition to C, we could call it, maybe we'll call it Z underscore. Okay, I'm calling it Z underscore because it's good to not use very simple, commonly needed variables X, Y, Z throughout your problem so that they're available for other applications. Okay, so now what about Z? Alright, let's go to this formula bar and let's put our formula here in. Let's see, looking at our original problem as formulated, it said that Z was equal to 0.6x. Now, I don't put x. I either have a choice of using the x vert. Since that name was long, I think just simply the a is pretty good. And I'm also going to put the times here, times a, the simpler name for that column. And then we're adding, we're subtracting 0.3y, so that will mean subtracting 0.3, and we'll use the b, since that's the name, the simpler name of the column that has the y coordinates here. Okay, and so we can go enter. Wanted to come up here and make this larger so that the formula can be read, and we don't need any other columns, so I think I'll just go ahead and expand that fully across the way there. Now, what about deciding what to do next? Well, the problem is reviewing the problem statement. Determine the minimum value of z. Okay, looks like it's right there. There's our number now. We're ready to start making a conclusion. Maybe I'll... Okay, let's go with Control C. And to write a conclusive statement, I think a new document page, we can go Control, Add Page, and Notes. This is like a text document here. So here we go then. We can say the minimum value of z is, okay, I have Control V, can paste that number here. Now we were supposed to be rounding all final answers to 3 significant digits, so here's our chance to be doing that. It looks like that should be negative 1.86, so do a little backspace here, make that 6, and I copied a little more than I needed to. I don't need that equal sign here. Okay, back up here, and I period to end the sentence. Now let's go ahead and go the extra distance here, although we don't actually have to. At x, y equal to. Okay, let's go ahead and collect that information. I guess we could use our memories here. Let's round these to 3 significant digits and then remember them instead of having to copy and paste. So to 3 significant digits, this x-coordinate would be negative 1.26. and the y-coordinate will be 3.67. Okay. So negative 1.26, comma 3.67. Okay. And there is our conclusive statement for the Part B of this question. A last little cosmetic touch-up on this feasible region graph before we put it into our final finished document, and that's this grid here, which was great for helping us find points that were clearly in our feasible region, is no longer necessary and maybe a little distracting. So what we can do is go to Menu, View, and high grid. There. Now capture it. Okay, so to complete our Part B solution, we could take those captured images from the Nspire calculator and put them all here on our solution page as what's been done here. The last thing I might do is, since here's our big conclusive statement, to make it a little more prominent, maybe some highlighting and something like this, big prominent cloud. So the conclusion really kind of jumps off the page there, and that would complete our Part B. Okay, Part C. Using calculator and or computer apps, illustrate this problem graphically. Okay, now since we are minimizing a function z here of two variables x and y, we need to go to a three-dimensional graph to really see the big picture of all this. So let's do that next. Okay, bring back our Nspire calculator, and let's see, when we last left off we had page 3 here. We will now go and add a page 4. This will be an adding graphs situation. And for our menu here, we want to view 3D graphing. Okay. The formula for z in this specific case, looking back at the problem, was z equal to, it was 0.6x minus 0.3y. Okay, now of course, since that was a linear function, we're expecting to see this plane in 3 space, which we do. A couple things. Maybe first that box, I think I will go ahead and remove that. So hide box. If we think about this a little bit, for a moment we could kind of let this revolve about, take a look at this plane. Okay, now another little touch-up we might want to do right now. Consider that the feasible region, the domain of this function, was almost entirely in quadrant 1. And in fact, we can sort of inspect the maximum and minimum x's and y's we need on the xy plane here. Looking at that feasible region again, looks like the x is ranging from about -2 to about 6 would work. Now, since that's 8 units of axis, I try to make all the axes 8 units. The y needs to go from, well, 0 to 7 or so, 0 to 8, I guess we'll say. And then the z-axis, well, let's see, we're looking at it now, looking like maybe kind of guessing -4 to +4 might be satisfactory there. Okay, so let's go ahead and go to the menu, get the range and zoom going, go to these range settings, and think about getting the feasible region placed on the xy plane there. An x-min of perhaps -2 would be nice there. And tab down, x-max, about a 6 seems to work out there. Scaling 1 unit apiece. The y-min, let's 0, just to make sure we get the x-axis to still appear. And tabbing down to a y-max of 8. Scale axis, the y-axis at 1 unit apiece. On the z-axis, okay, maybe we try -4 to +4. Just kind of looking at that. Okay, scale at 1 unit per tick mark, although the tick marks will not appear here. And the otherwise, we can rotate it when we take a look at our results. So let's get to the point of okaying this. Enter. Alright, this is a little better. Now let's see here, maybe we stop this fast rotation, and we can actually kind of spin it ourselves here with our cursor on the computer anyway. Let's see what would look nice. You kind of want to get that region in sight, and let's see, this might be better here. It's very subjective, of course. Okay, perhaps about there, and in which case we could now do a screen capture, and then take this image and work with perhaps Microsoft Paint to put in the domain and be able to sketch the actual function from this large plane surface here. Okay, here's the final result. Here in the green is the function under study. That is the plane quadrilateral whose equation is here the z equals 0.6x minus 0.3y. It's a quadrilateral plane in 3 space, and you know, this actually slices through the xy plane when, well, z equals 0. If you set this equal to 0, 0.6x minus 0.3y, and then simplify it, it actually turns out to be y equals 2x. And that little slice-through line is the dashed red line here. And so that helps explain why two of our z values were positive, corresponding to this vertex and this vertex, both lying above the xy plane. And we had 2 negative vertice values here and over here. The minimum value of z was the negative 1.86, occurring at this occurs at this point here. This is the actual graph of z, and this actually makes a kind of a check on our answer, because this does indeed appear to be the lowest point on this plane quadrilateral. Okay, there we are, the 3D interpretation of this question. Exercise 23. Consider the following problem. Determine the minimum value of z, where z equals 8x to the 4th divided by 3 plus y to the 4th divided by 3 plus 16x cubed minus 5y cubed over 2 plus 4y squared plus 55x squared. Subject to x greater than or equal to negative 5 and less than or equal to 5, and y greater than or equal to 0 and less than or equal to 10. Part A. Is this a linear programming problem? Explain the basis of your conclusion. Alright, as you read this problem, well, it is an optimization problem. Determine the minimum value of z. But look at this formulation of z. And quite a few problems with being linear, that's for sure. Okay, many terms here in this formulation that disqualify z from being a linear function, and if that's the case, then this is not a linear programming problem. Okay, so let's record that. Okay, so that we've written, no, this is not a linear programming problem. The reason is that the function is not linear. Okay, let's go to part B. If this is a linear programming problem, solve it with assistance from the TI Nspire CX. Well, it's not a linear programming problem, so as far as we're concerned, this part B, we could write here, not applicable. Okay. Part C. If this is not a linear programming problem, solve a graphic approximation with assistance from the TI Nspire CX. Attempt to record all final numbers to 2 significant digits. Okay, let's try this out. Let's choose to add a graph. Now, we've seen the formulation of this function that we're looking at here. It's z as a function of 2 variables. We need to go to a 3D graph. So Menu, View, 3D Graphing. Okay, here in the Z1 box, we record the formulation. We've got 8x caret for exponentiation. We have the 4th power. We go to a forward arrow to escape the exponentiation box. Then it's a plus, and we have here y caret 4. Forward arrow to escape the exponentiation box, and this is all divided by 3. Then we go on with plus 16 x cubed. Okay, x caret and 3, forward arrow to escape exponentiation. Then we have minus 5y cubed over 2. Okay, minus 5 y caret cubed, forward arrow, divided by 2, then plus 4y squared plus 55x squared. Okay, there's the formulation for z. Now, that's just the formulation. Looking at the domain, there were a number of linear inequalities here constraining us. The first one is written as a compound inequality. Okay, we have here x greater than or equal to negative 5 and x less than or equal to 5. Okay, for that, we go here to the range. Let's go to those range settings. Alright, the way this is set up as default has x min negative 5, x max 5. That happens to be just what we want. Okay. Scaling, maybe we pick one apiece for this axis. Let's tab forward to the x range, rather the y range, and in the y range we go from 0 for a y min to 10 for a y max. May choose to scale here at 1 unit per tick mark. Now z we don't know too much about here. Alright, so I suppose we could just leave the default. And by the way, there is something to consider here, and that's that this 3D graphing app really works best when all the axes have the same length. So right now, the x-axis is 10 units long, the y-axis is 10 units long, so the z-axis, at least it is 10 units long. So at least we will get a reasonable looking graph when we finish here, and maybe we can scale the z-axis at 1 per tick mark. Okay, there. And now let's go ahead and hit enter to put in our formulation for z, and this appears here. Okay, let's see what to think about this. We could go look at what we've got. Now, this looks like a rather small portion of the graph of this function. We see a lot of empty space here, although we do see the graph having some interesting appearance in this area here. Okay, let's see. To get more of the graph, what could we do here? You might think, oh, let's make the z-axis much larger. And the trouble with that is that if you make the z-axis much larger, the program, the application here, will force the x and y-axis to be scaled similarly. In other words, the distance between one unit always remains the same on the x, y, and z axis. So if we make z go from, well, let's try something to demonstrate this. Let's change z axis. Go down here. All right. Let's suppose we would say, oh, you know what would be nice? Maybe let z go from negative 100, negative 100, tab, and 100. Maybe this will show us a lot more graph. And so you decide you do that. You go OK, and you get something like this. Okay, the trouble is that the distance between one unit going from negative 100 to positive 100 is going to stay the same on the x and y axis, which means those x and y axes shrink down to something you really can't even see. So this is not a good idea. Let's try something else. Let's go back and change that. That was just to demonstrate how you don't want to make the axes to be of significantly different lengths. So for right now, maybe we could just stick with a negative 5 for the z-min and the 5 for the z-max. Go back to where we were. Okay, how can we get the sort of the entire graph to appear? Alright, here's another idea. Right now we have in our formulation z. What we could do is consider shrinking z towards the xy plane. And how can we do that? We can go here to the formulation, and we can go up here to our function. Okay, Now, let's, instead of having this, let's take this and divide it all by 100. Let's try that. So parenthesis, okay, right parenthesis, and now we will do a divided by, and let's say 100. And enter. Okay, now we are starting to see a lot more graph, a lot more of the overall picture. Not bad. Now the trouble is we still don't have enough because we've already set the x and y axes so that they reflect the domain of the function, and yet we still have a very large portion of the xy plane for which there is no graph above or below it. So we're still missing quite a bit. There might be some real interesting things here. We don't know. There's only another way to find out, and that is to perhaps try this same strategy to a greater degree. In other words, let's go to tab, and then we can arrow up, and let's go here and divide it by 1,000. Okay, enter. Okay, now we seem to be getting somewhere. We are looking pretty good. Looks like what we could do to get perhaps the last portion of graph to entirely appear is now we actually could change the z-axis. It looks like we don't need to go down here to -5. If we sort of look down here, it looks like we need very little negative for z at all. So okay, let's go from -1 to 9 on the z-axis. Okay, -1, and then z-max could be 9. Okay, alright, there we are. Now this looks pretty complete. If we stare at this from the top, we see that we've got the entire xy plane, at least in the domain, as having points above it. So this is the complete graph of the function, not missing anything. Now it's a rather large scale graph. Now there's a, how do we do this? We had to reset the function to be 1/1000th of its actual formulation. But you know what? We can still consider this the graph of the function. And how can we do that? Because what we do is we realize that we made this formulation to be the f of xy 1/1000th of the original z. Well, we could now instead put the scaling on the axis. Instead of -1 to 9, multiply those numbers by 1,000, -100 to 900, and then this is the graph of original z. But by doing that, so it's kind of a clever way to get the actual graph of this while still maintaining the same size for each axis. So again, the idea was it just shrinks z as needed by dividing it by various powers of 10. We had to go to 1,000 to get it all to appear. And then what we can do is we'll just label our axes by multiplying the scale numbers by 1,000. That way we have here the original function on a graph. Okay, so now I'm going to get ready to capture this image. I think, let's see, I want to put it into a position that looks kind of nice. And a lot of times I tend to get rid of the box when I'm trying to get a picture of the actual graph itself. I will just put the labels right on the axes with another application. So, wait, not there. Escape this. Menu, View, Hide Box. Okay, there. That looks kind of nice. Okay, so maybe we could even zoom in a little bit here. Okay, that looks pretty good. And perhaps take a capture picture of this so that we don't forget how we have scaled the axes to obtain this picture. Maybe it's a good idea to go to the menu and go to the range settings, and capture their picture as well. It takes 2 pictures to get everything, so we could capture the page, scroll down to show what our we need the z-axis information anyway. Capture that page. Okay, that's set. Now we have the graph of this entire function sitting before us. Looks pretty nice. Now the next thing we need to do is work on approximating the minimum value. Okay, for that we almost need to go back now and take a look at a sort of a zoomed in version of this graph. Okay, to do that, maybe we actually go back and take away the shrinking from the formulation of z. In other words, let's go back here to our formula up here, and maybe we actually initially, let's take away this whole thing here for a minute. If we think back to that first graph, we still couldn't. We had a function where we couldn't see the z-min at all. So perhaps we do divide this by maybe 10 at least to get started on this endeavor. Alright, let's try that much. Alright, this brings us to here. Now this starts to get us in position to get a good zoomed in idea of where this minimum of this function seems to be. Let's see, if we look here on the bottom, you can, well, maybe from here this is a little more clear. Alright, so it's down around there. We can do a little bit more to work on this. Let's see, based on this information we have here, we don't need so much y-axis and we don't need so much x-axis anymore. It looks like that minimum there looks around y. Now remember, right now y goes from 0 to 10. Right around here looks like it's about y around 4ish. Okay, and the x, we're looking down here, the x looks to be like right on the y-axis, so its x is about 0. And the z right now, if we think back to our scaling, is around -1 or so. Okay, so you know what we do? Let's sort of zoom in by changing the axes, centering matters around this point here, which looks to be about 0, 4, -1. So we can go to the menu, the range settings. Now if I want to have matters closed in near x equal to 0, I'll say x min -1, x max +1. We could do something like that. Okay, -1, +1. Scaling at this size, maybe just 0.1, 1/10 per unit on the x-axis. Okay, the y-axis, we were thinking centering things around 4 to be zooming in close, so between 3 and 5. 3, tab, 5. Okay, now on the z-axis, it looks like centering matters around z equal to -1, so that means a z-min of -2 and a z-max is 0. This way -1 is right in between there. So right now, each axis is the same length, 2 units long, and yet we are going to be zooming in on the part of the graph that seems to contain the minimum point from what we're seeing right now. By the way, the z-scaling, let's make that 1/10 as well. Okay. So now we're here. Okay. Not bad. You know what? Because now we start to want to see scaling, it might be a good idea to actually bring back that box. So menu, view, and let's show that box. Okay. This will help us decide what we think the various coordinates are. Now, as far as getting to that minimum point here, here's a nice idea that the calculator has. We could go here to the menu, go with tracing, a z-trace. Alright, now this slices a horizontal plane through. It tells you what the equation of that horizontal plane is. Z equal to a constant is always what goes on for a horizontal plane. And right now we have z equal to a -1. We might look at what we have here. You know what? It might be best to look at the bottom. Well, first let me show you what this does, what you can do with this as it stands right now. Okay, you can move this plane up and down. Do so by either going Shift up. See, now Z went up, increased to 0.9, or you can Shift down to bring it down. Now, since we're trying to cite out this minimum point, going down looks like a good idea for us. Okay, so we've almost gone too far right now. In fact, we seem to be, well, maybe not. It's very close. We're very near the bottom. Maybe we're there. You know what? Maybe we zoom in one more level. Let's see what point we seem to have right now. Looks like Z, very close to -1. The X, just looking at this here, okay, the X right in here looks like it's very, very close to 0. And the Y, maybe we look at the side to get a Y. Okay, now there's Y3, there's a Y5. We're here, so in the middle would be 4. It looks like about 4.2. Alright, it looks like we seem to have the point 0, 4.2, and -1.0 or so. Let's zoom in further. One more stage. Alright, so getting really close to that X equal to 0. Let's make the axes only 2/10 in size. So we'll say -0.1, 0.1, scaling, let's see, maybe 0.01 in this case. For Y, alright, we're going to close in very close to 4.2, so we'll say 4.1 for min, 4.3 for the max, scale at 0.01. Now Z, looking very close to a -1 or -1.1, we could say -1.2 for its min, and then we can go with -1.0 for the max. And the scaling, 0.01, 1/100th between tick marks. Okay, this brings us here. Now let's go back and move this plane a little bit. Now right now the plane may move a little bit too much between jumps because we haven't reset it. Let's see what happens right now. If I go Shift up 1, okay, see, it's going up a lot. No problem. Just do this. Go to the menu, the tracing, the trace setup. Here you can set up how many steps that plane moves to go across the entire z-axis you have illustrated. Right now we have it set at 20, which is good, except for right now it's sticking with its 20 steps from the last coordinate system. We just need to go here and kind of like reset it to this situation by hitting OK there. Now if we try doing a Shift up, for instance, here, let's look down here. Let's bring this plane so that it starts to be touching the graph there. So Shift up. Wow, okay, that's definitely a hit. And if we go with a Shift down, we seem to be missing the graph there. Okay, so it looks like, okay, looks like a z equal to -1.1 is apparently our minimal z, careful, minimal z based on the formulation where we have, well, let's look back at what we have. See that? Right now we have a z equal to the original formula divided by 10. No problem. just have to remember to multiply that z-coordinate by 10 to recover what it really is. In other words, that negative 1.1, that's a negative 11 for the original function. Okay, now the x and y stay the same, so let's get rid of that for a minute. Let's go back here. Let's bring back our plane. Okay, so it's shift up. Alright, now you might think that by shifting up that one little bit, we actually intersected quite a bit of the graph. How can we make the upward shift not so great? Alright, we know how to do that. Let's go back to the trace setup. Instead of 20 steps on the tracing, maybe we make it 100. This will give us a lot more finer control over the movement of that trace. Okay, click 100. Now, let's start climbing up a little bit from here. That means shift up. Okay, shift up. Okay, shift up. Alright, we're just starting to see a little bit of those wires. Alright, I like to see actually pink graph, because the wires are not necessarily the graph itself, they're just to help you see the graph. So we want to see a little bit of pink here, or a little bit of red. Let's go a little more high. Control Shift. Okay, now that's a pretty clear intersection there, and it's not so large. So let's see, what do we think here? Looks like the X, alright, right in the middle. X is about 0 pretty much. Go with that. For Y, let's see what we think about Y. Let's get a scaled Y here. Here's Y 4.1, there's Y 4.3. It looks like the sort of the middle of this intersected region is right between here. That would be about Y 4.2. Alright, we are ready for a conclusion on the minimum pointer Y. Let's go ahead and record what we have. Okay, here's our final image after a little bit of work with the Microsoft Paint. In the upper left is the original function, the overall function graph. Now you notice it's been labeled with the original formulation, but you know that actually to get that we took z divided it by 1,000. However, that's compensated for because look at the way the z-axis is labeled. The negative 1 to 9, multiply all the coordinates by 1,000, and you have indeed the actual case of what's going on there. In the case of the negative 1, I couldn't fit negative 1, so I extended the axis down a little further and labeled a negative 2,000 coordinate on that z-axis. The x and y are as originally put into the calculator. Then, zooming in on a certain section, a little oval, shows where we're zooming in on, and from this little zoom in, we actually come up with the approximation of the minimum point there. We found 0, 4.2, negative 11, and again, a little device here. When we had this on the calculator, our z-axis was negative 1.0 to negative 1.2. However, the formulation was a z formula there divided by 10. So what we can do is still consider this the actual original graph of z, but take the z-axis and multiply it by 10 to compensate for what's been done to the formula. Okay, so good approximate conclusion. And by the way, if you were to proceed to Calculus 3, where there are calculus methods to solve this same problem, you'd find that our approximation here is actually indeed accurate to its two significant digits that have been stated. Okay, very good.